my name is Aleksandar Dimić, and on behalf of my colleagues from the Faculty of Mechanical Engineering, from Innovation Center of the Faculty of Mechanical Engineering, and from company EDFO, I will present the paper on the subject of windage losses of the high-speed cylindrical tubes. So here on the presentation, we can see the spread of mechanical drives towards the end of the 2005 year, but that trend is still present. So there is a great importance to let's say, to upgrade the calculation processes, to thermal processes, finishing processes of the cylindrical gear drives, because they occupy approximately 50% of all mechanical drive. So as the main causes of power loss for any gear drive, we have tooth mesh friction, churning of oil, windage losses, oil pocketing, and gears back. And as we will see later, the main losses for the high-speed gearing is windage losses. And when I say high-speed gearing, I think on the gears which have pitch velocity around more than 60 meters per second. So the windage loss is power loss, which generates due to fluid drag experienced by the gear teeth addendum, let's say, when it's running in the combination of air and oil. So here on the slide, we can see some simulation of the turbulent flow on the gear teeth addendum. And that is the main reason for the generation of losses, which can be significant for the high-speed gear. On the right side of the slide, we can see the one of the possible solution for the windage losses, and it's called shrouding. When we limit the area above the gear addendum, so that we hope that we can transform this turbulent flow into the laminar flow and reduce the losses to that kind. So 4 models have been analyzed. First model, the oldest, is Dawson's model. So it takes into account it is done experimentally. The model is formed on the basis of experimental results, but those experiments have been made for the spar gears. So that can be the problem when you want to apply these results for the helical gearing. And here we can see the equation which he gets when testing the spar gears, and also the quantities which are taken into account when we want to calculate the power loss on the basis of this model. So the next model was Anderson and Lowenthal model. It is done for the turbine rotor wheel, and also based on experiments, and it has taken into account also the density of the atmosphere and viscosity of the mixed atmosphere of oil and air which is present in the gearbox. So for the third model, it is also Dawson, but now in his next experiments, he took into account the influence of the helical angle. So here the basic quantity for this equation, which can give us the windage losses, is given on the presentation. The main gear parameters, let's say. And fourth module, error, but the fourth model is the latest one. It is formula presented by Dia, and it takes into account separate gear losses for the gear phase contribution and the contribution of the gear teeth. So the models are somehow complicated, and I won't lose any time for that. You can see the main influence for every equation, and now the application of this model has been done for the gearbox used in aircraft industry. That's a gearbox which turbo shaft jet engine, which takes the energy from the rotation of the turbine motor. So here is the configuration of the gearbox which was analyzed. I want to express that the entrance rotational speed of the gear number 1 is 40,000 RPM. So very, very big rotational speed, which is then transferred to the rest of the gear pairs, so that we at the output shaft of the gearbox, we have 250 RPM. So that is a two-step big reduction made by the split path configuration of the gearbox. The analyzed gear for this specific analysis was gear number 2, because in addition to high RPM, 10,000 RPM, it also have big diameter. So we identify the gear number 2 as the most influenced by the windage losses, and in the table next to the configuration of the gearbox, the main quantities are given: number of teeth, nodule, profile angle, helix angle, and stuff like that. So when we calculated the losses on the basis of 4 models, which I briefly represented, we get the diagram on our left side. So we can see that there is a big scatter in the results. And the exponential rise of these functions is expected about 5,000 RPM. In addition to this, we also calculated the meshing losses of the gear. So that is the linear loss diagram on the upper right side of the slide. And we somehow wanted to compare these losses. We wanted to know the influence, the ratio of the windage to gear meshing power losses. So we expressed we made the average, we took into account all 4 represented models, and we made average function which takes into account all 4 analyzed models. So we called it the C parameter, which gives us the ratio of the losses during the meshing and losses during the windage. And the diagram on the right side is the distributions of these losses. So we can see that the lower and upper average values are given, but the black line represents the mean value of factor C. And we can say that for the 10,000 RPM, the expected losses are about 20% in regards to the meshing power losses of the gear. So that is something which is not small losses. So we can expect some heating as a consequence of that and stuff. So the main conclusions are that we get the exponential growth in relation to the revolutions per minute, but significant losses are expected over the 6,000 RPM or 45 pitch velocity of 45 meters per second. Model number 2 is the most rigorous and gives us the highest windage losses of 360 watts. So we can calculate that in temperature, and we can calculate the expected rise in temperature. In relation to meshing losses, the proportion of windage losses are about from 4 to 34, but as I said, the 20% is somehow expected. And we try to introduce the general factor C, which takes into account all analyzed models and give us the ratio of losses in accordance to the rotations per minute for energy. So in the next phases, we want to test the results. So in that manner, we made some. On the left side, you can see some high-speed helical gears used in the aircraft industry, and we made these like shroud segments, which tends to decrease the gap between the gear tip and the housing. So we want to test, can we lower the windage losses for the high-speed gearing you used in the aircraft industry. So on the right side of the slide, here, this is the gearbox and only turbine is attached. We tested the gearbox, but in reverse. We gave him rotational speed on the electron motor, and the only torque that happened in the gearbox is from the air resistance of the turbine. That was our first test. Here should be some video, but I don't know if it's on. And the end testing should be done with the hydraulic brake, where we will definitely confirm whether these calculations are correct or not. So we will confirm if our model gives good predictions. So because I used some reference, I gave them